we will continue our discussion with chapter 14, particle kinetics, work and energy. So this part we will learn about power and efficiency, and then later part we will see something about conservative and non-conservative force. So power and efficiency. What is power? The term power provides a useful basis for choosing the type of motor or machine which is required to do certain amount of work in given time. In general, power is given by work divided by time. If you are doing same amount of work in less time, it means you are applying more power. If you are doing same amount of work in more time, if you are taking extra time, then you have less power. So less the time, more the power, more the time, less the power. So power is work divided by time, du by dt. U is our work, time t dt there. We know that this work done is nothing but force into displacement. Du is F into dr. F is force, dr is displacement. So I'm going to take this F into dr, I'm going to put it in here, and if I do that, I'll get power is equal to F dr by dt. This dr by dt is nothing but distance upon time, that's nothing but your velocity. So what I get, the definition of power is equal to force into velocity, and that's it. If you are applying force, there is some displacement and your velocity is very high. In that case, you are applying more power. If your velocity is low, in that case you are applying less power. So power is directly proportional to force and velocity. Force into velocity is nothing but power. Also, important thing about power is force is a vector. Velocity is also vector, and dot product of two vectors is a scalar. So power is basically a scalar. All you need is a magnitude, you don't need direction. So that's your power, force into velocity. The unit, SI unit for power is watts, or 1 joule per second, or Newton meter per second. So this is your SI unit for power. Some other unit normally is used in the past is horsepower. Horsepower, 1 horsepower is normally 550 pound-foot per second, or if I want to have conversion, 1 horsepower is 746 watts. Now this horsepower term, in the past they used to use horses. So if we have one average size horse lifting almost 75 kilogram of weight for 1 meter height in 1 second, that will be almost equal to 746 watts. So that's the general idea how much one average size horse can generate a power, and that will be 1 horsepower 746 watts. So, and then we have efficiency. So power is nothing but work divided by time, or force into velocity. And then we have efficiency. Efficiency is power output upon input. If you have any machine, let's say electrical motor, or if you have an engine, you need to have some kind of input energy or input power, and then that machine will give you some output. So the ratio of that output divided by input is simply efficiency. That's energy input by energy output by energy input, or power output by power input. This efficiency is always less than 1. That's your second law of thermodynamics. Whatever happens, any machine cannot perform with 100% or more efficiency. You are going to get 80%, 70%, 90%. If it is a thermal engine, you are going to get 40 or 50% efficiency. So that's your efficiency, output upon input. Now for power, let's solve a problem. This problem is from the book. It's a very simple problem. What we have in this problem is a man pushing this 50 kilogram crate. So this is a 50 kilogram crate he's going to push, and the force he's applying is 150 Newton at an angle. So there is some kind of an angle, and then he's pushing that box with that angle. What we want to find out is determine the power supplied by the man when t is equal to 4 seconds. So he starts from the rest, and he's going to start to push with 0. Initially the initial velocity is 0, and then t is equal to 0 second he starts push, and then at t equal to 4 seconds he's going to continue to push, but at 4 second mark we want to find how much power is supplied by this man, and that's the problem. The other information is given is kinetic friction between the floor and the crate is 0.2. So whatever the friction is happening here is 0.2, and initially crate is at rest, so he's starting from 0 velocity. That's the information. So here Our objective is to calculate power, force into velocity. We have a force. Whatever horizontal component of this force will contribute in the power, it will contribute in work done. Whatever vertical component will not contribute in work done. So 150 Newton into angle, whatever cos angle is, so 150 cos theta, that's a force. We want to find out velocity. Without velocity, we can solve this. So objective in this problem is to calculate velocity. So for that, first we will set up our coordinate system, xy coordinate system, x rightward positive, y upward positive. Once I have that xy coordinate system, I'm going to draw free body diagram. Free body diagram here, weight acting downwards 50 into weight 9.81, normal reaction upward, and then as the movement on this side, the frictional force is on opposite side, 0.2 of normal reaction. So 0.2 my coefficient and then into normal, that's my friction, and the force applied 150 Newton at an angle. That's my free body diagram. So now this is a kind of a chapter 13 method again. So once we draw a free body diagram, here I need to know angle. So angle is directly not given. What is given is geometry here 3, 4, 5, and based on that I can safely say, of course I can resolve these force here, f cos theta and f sin theta. Our objective is to know f cos theta is whatever f cos theta here, we have to use that. So we need to know theta, and in order to know theta, if I use this geometry, I can safely say that tan theta is 3 by 4. So this side by this side 3 by 4 is this theta, tan theta. That's the angle. And once I have tan theta, or theta is equal to tan inverse 3 by 4, and then 67 degrees or something kind of value you will get. So theta is equal to tan inverse 3 by 4. That's your theta here, f cos theta. And now once I'm done with free body diagram, once I know what angle is, I can apply my equation of motion. So here my equation of motion, summation of all forces in x direction, max, that's acceleration in x direction, and summation of all forces in y direction, may. Acceleration in y direction is 0. So this entire term is 0 because there is no y acceleration. Now all we have to do is that it's the same thing, chapter 13 method, you can do it at home. All the forces in x direction, f cos theta positive minus 0.2 Newton negative is equal to max. We don't have value of ax. And same way here we want to find out fy will be normal positive, downward weight negative, and again minus f sin theta here, that will be negative, and may will be 0. So here there are two unknowns. We have normal, we don't have, and ax we don't have. So the objective is to solve these two simultaneous equations and calculate acceleration. Once you calculate acceleration, you can calculate velocity. So this is chapter 12 equation, kinematic equation we are going to use. V is equal to initial velocity 0, acceleration into time. Time is 4 seconds. So the objective here is to calculate acceleration. Once you have acceleration, put that here, calculate velocity. Once you have velocity, use this velocity here, and that's my fv or fxv, that's my x directional force I am going to use, that's my velocity. Power is equal to f cos theta into velocity. Use that velocity and calculate power, and that's the objective. So if you have time at home, take the calculator to solve this simultaneous equation and calculate normal and calculate acceleration. So I'm going to do this calculation here. Normal, if you calculate, it will come 580.5 Newton, and then acceleration will come 0.078 meter per second square. Once we have this acceleration, I'm going to take this value 0.078, I'm going to put it here. Once I put it here, I have time into 4. So this into time 4, that will give me a velocity. Velocity at 4 second mark is 0.312 meter per second. That's it. So I'm going to take this value of velocity, I'm going to put it here, f cos theta into 0.312, that's my velocity, and then if I do that, I'll get final value for the power is 37.4 watts. It means at 4 second mark, this man is applied the value of 37.4 watts. That's the answer. Now you may ask question, why we use fx here, all the forces, why we are not using here this part, force in opposite direction? The reason is that we have already understood this force here to calculate velocity. So this force, frictional force in opposite direction is already considered here, and based on that force we have velocity. And now, as we are already considered, in this case we are going to consider only x directional force. Fx is into v. So Fx is f cos theta, that's 150 cos theta into velocity is 0.312, and that will come as 37.4 watts, and that's the final answer for this kind of problem. This is a solved problem from the book. If you want, you can practice this problem by changing the angle, by changing this force, by changing the weight of this one, and then you can see how much power goes up or down, what happens altogether. You can practice that way. Let's do the next part, conservative forces and potential energy. In general, I can classify all the forces into two parts. One is conservative force and another is non-conservative force. So, conservative force, in general, I can say that conservative force is force which depend on overall path followed. It's not depend on path followed, so only initial and final position is there. So whatever initial position, final position, it depends, and that's your conservative force. There is another example for non-conservative force, is it depends on path followed, such as frictional force. If there is a friction, then it will matter what kind of path is followed. But in general, potential energy such as gravitational energy or spring potential energy, you don't need what path followed, you need final and initial state. If you are just dealing with final and initial state, then you can call that force as conservative force. And one of the example for conservative force is potential energy. That's your gravitational potential energy and your spring potential energy. So what is potential energy? The ability of a force to do work depending on its position. That's your potential energy. So let's say I have an object falling down here on this path. So potential energy, as far as potential energy is concerned, it doesn't depend on what path is followed. The energy only depends on the position, the respective datum. So if this is my datum, potential energy here upward positive, respective to the datum, potential energy here will be negative. Whatever happens, the difference between this potential energy, this potential energy, this potential energy will stay constant. The formula for potential energy is mgh, mass into gravity into height, or mass into gravity is nothing but weight, so I can say weight into height, or wz. Another way I can rewrite it as weight into y. In general, if I am using xyz coordinate system, then y is my height, so I am going to put that here mg into y or w into y. That will be my potential energy. Another important thing about potential energy, the symbol that we use here for potential energy is V. If you remember, for kinetic energy we use symbol T. For potential energy we use symbol V, and if it is potential energy associated with gravity, in that case we use G. So Vg is your gravitational potential energy. Now once we done with the gravitational potential energy, there is another potential energy as spring potential energy or elastic potential energy. Elastic potential energy is given by the letter VE. V is potential energy and E is elastic potential. So VE is nothing but my elastic potential energy, that's ability of spring force to do work. So I have a spring here. Initially it is in unstretched position, and now either I am going to compress it or I am going to stretch it. Either way there will be potential energy associated with spring. If I am going to compress it, I am going to take that value as minus S1 from this unstretched position. If I am going to stretch it, I am going to take that value of S2 positive from unstretched position S2. Now the formula for potential energy is VE is equal to 1/2 Ks square. K is your spring constant. Normally it's given in the problem, and S is your position. So it could be either S1 or S2. If you see that K is always positive and S square is going to stay always positive, because S1 could be negative, but the square of S1 could be always positive. So one thing, important thing about potential energy is that it is always non-negative or it is always positive. So keep that in mind, and that's the formula that we use for potential energy, 1/2 Ks square. So combination of these two energies, you have potential energy and you have gravitational potential energy and you have elastic potential energy. Combination of these two things we call potential function. So that's my gravitational potential energy, elastic potential energy combined. I'm going to say simple V, capital V. Don't get confused with small v. Small v is velocity. Capital V is my potential function, combination of gravitational potential and elastic potential energy. For example, let's say I have a large mass here, 10 kg is associated with this spring. So gravity is trying to pull it down. At the same time, spring will try to pull it up. And then this is a combination of two forces. So whatever the movement of this one up or down, whatever the movement is combination of two forces here. That's spring potential and gravitational potential, and that will be my potential function. And the work done overall in this process is given by U12 is V1 minus V2. That's my initial potential function minus final potential function, and that will give you me total work done U12. From position 1 to position 2, I can find out the total work done by these potential function, by these two energies. Now, if you remember, in the last class, in the last video, we learned about principle of work and energy. T1, that's your initial kinetic energy, and your work done, and then you reach to final kinetic energy. That's principle of work and energy. Now we learn potential function or combination, potential function here, work done by potential function or work done with potential energy is, your work done is equal to V1 minus V2. That's your initial potential energy minus final potential energy. Now if you look at here, I have U12 here, I have U12 here, that's my work done. So what I'm going to do, I'm going to take this value, I'm going to plug it here, and I'm going to rewrite this entire equation. So I will get T1 plus V1 minus V2 is equal to T2. So this minus V2, I'm going to take it here, and then I'm going to rewrite the equation. If I do that, the equation will look something like this. T1 V1 is equal to T2 V2. What is it? Initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. If there is a system, if I'm not considering non-conservative things such as friction, then what it says that all the energy in the system is conserved. So whatever initial state, whatever initial energy of the system is nothing but final energy of the system. Meanwhile, energy can convert into one form into another, but overall energy of the system will stay constant, and that's what the formula is. This is conservative forces at work, and that's what we can call it as conservation of mechanical energy or conservation of energy principle. So all we know is here is that overall energy of the system is conserved. Now how we can imagine this formula? Let's say I have a pendulum. Now what I'm going to do, this is my lowest point for the pendulum, this is the highest possible point for the pendulum. I'm going to take this pendulum, I'm going to hold at this point. I'm not going to release it, I'm going to hold it. So as soon as I hold it, this pendulum has some potential energy with respect to this position. So this is my final position or bottommost position. Here I have highest potential energy, and now I'm going to release it. As soon as I release it, all that potential energy is converted into kinetic energy, and then it will reach at this position. Now at this position it will have zero potential energy and highest kinetic energy, it means highest velocity. All that kinetic energy again will convert into potential energy, it will go here, it will stop, and then it will come back again, so on and so forth. If there is no friction at all, there is no air, in that case this thing will go forever and ever. So what we can say is the position 1, position 2, again position 1, position 2, so on and so forth. So initial potential energy and kinetic energy here, whatever happens, this when it reaches at position 2, your potential energy will become 0, highest kinetic energy, and then this thing will go on and go on. So that's how we can see this principle in happening. For a system of particles, if you are dealing with more than one particle, now this is only one particle, if they are dealing with more than one particle in the system, in that case you are going to add all these energies of the system, all the kinetic energies and all the potential energy of the system is going to stay same. In the final state, all the final kinetic energy and final potential energy is going to stay constant. So this is the part we apply system of particle. In general, every time we have something called system of particle, we apply this summation sign, and then we can rewrite the same equation. So that's how we can do it for system of particle. Let's solve a problem. Now in this problem, what we have is a collar, a 10 kilogram collar here, 10 kilogram collar. It travels down on smooth slope, there is no friction. So this collar is coming down like this, and there are two forces applied on the collar. One is gravity downward and another is spring force. So spring is trying to pull it like this, and then gravity is trying to pull it down, and because of these two forces, and also it has some initial velocity, downward direction 20 meters per second. So it's coming down with 20 meter per second here, and slope of this surface is given. Whatever the slope here is given, y is equal to 154 x3 by 2. That's the equation of this thing is given. So we know the equation, we know the path followed. This is going to come slide down like this. What we want to know is that if this is position 1, at position 2, what is its velocity? So it's going to come down, and it's still going to come down for some time, but at this position, when x is equal to 10 meters, we want to find out velocity. That's the problem here. So when it gets to point 2, S2, find out position. The spring remains horizontal, so entire thing, the spring is going to come down like this, it's going to stay horizontal, and it has original length of 8 meter unstretched position. So the spring's unstretched position is 8 meters somewhere here. It means that it's going to come here, and most likely it's going to stop. But before coming here, at this point when x is equal to 10 meter, we want to find out velocity. Spring constant K is 40 Newton per meter is given. Now for that, we are going to first use this equation, T1 V1 is equal to T2 V2. So the idea is that whatever energy, potential and kinetic energy at this point is going to stay same, potential and kinetic energy at this point. So calculate that energy, calculate that kinetic energy, especially kinetic energy is T2, and once you have that kinetic energy, you can calculate velocity. So that's the idea, find out kinetic energy, and once you have kinetic energy, T2, find out V2, 1/2 and V2 square. So that's overall the process is. So to find out T2, we need the value for T1, which is this, we need value for V1, and we need value for V2. V1 and V2 are potential energies associated with gravity and spring at position 1 and position 2. So here V1 and V2 is potential and kinetic energy, potential energy for spring, potential energy for gravity, V1, and then here at final stage. So to calculate V1 and V2, we have to find out this part, then initial and final, potential and spring, and final potential and spring energies. That's what the problem is. To calculate V1, V2, put that value here, calculate T1. Once you have all three values, calculate T2. T2 is nothing but 1/2 mv2 square. From that, calculate V2. So to calculate these four things, four potential energies, we have formulas. So initial formula is that Vg1, that's my gravitational potential energy initially at this point, is Wy1 mg, and to height, this is height 2. So whatever this height we need to find out. To calculate this height, we are going to use this formula. So you have to put x is equal to 16 here and x is equal to 10 here. If you do that, you will get value for y1 and y2. Once you have values for y1 and y2, you can calculate Vg1 and Vg2, that is this part and this part. Once you're done with that, you have to calculate V1 and V2, that's 1/2 ks1 square, 1/2 ks2 square. The value for s1 and s2 is from unstretched position. Unstretched position is 8 meters. So S2 will become 10 minus 8, S1 will become 10 minus 8, 16 minus 8. So this one is 16 minus 8, so S1 will be 8, and S2 will be 10 minus 8, so S2 will be 2. So you have to make sure you know what is S1, what is S2. And then you have to calculate 1, 2, 3, 4 here. You will get V1, V2, put that value here, and calculate T2. Once you have T2, calculate velocity, and that's the problem. It's very simple, all the calculation. So if you have time, pause the video, do this calculation. If not, we are going to continue with this calculation. So now you need to know all these values. So here first T1 is 1/2 mv1 square. You have velocity 20 meter per second here. V1, I'm going to put that here, 2000 joule. That's the value for T1. And then the rest of the values, I'm just going to do this calculation. So here Vg1 will get your mgy1, that's the height here you have to find out. That's your gravitational potential energy, that's your elastic potential energy at point 1. And then as it comes down, you have gravitational and elastic potential energy here. So once you do that, I'm going to take these values of V1 and V2 all together, and then I'm going to put it here and here, and then I can calculate T2. So here T2 whatever the value T2 here is 1/2 mv2 square, and then I can calculate V2. So if I do all that, if I put all the numbers in, all the potential energy, gravitational energy, kinetic energy, all the numbers in, then I will get the value for V2 as 28.3 meter per second. What does it mean? We start with that 20 meter per second here. It's going to come down at this point when x is equal to 10. The value for this one is 28.3 meter per second. That's it. We're done with the problem. Alright then, let's move on to the next problem. Again, practice this problem, change some numbers, change the spring constant, change these parameters and see what kind of answers you get. You can do that while you practice for this problem. Now let's do another problem. In this problem, what we have is one giant structure which is used for plane crash testing. A small plane of 8,000 kilogram. We have to crash test it. So what we are going to do is that in that structure there is a rope, and this plane is connected to this rope, 20 meter rope, and then at some height from the bottom it's there. I'm going to keep it there with another rope AC, and now this is at rest, zero velocity. I'm going to cut this AC, and if I do that, this is going to swing down, and once it swings down, this is going to come here and it's going to crash here. In this problem, what we want to do is find out what is the velocity at this point. That's the first part, and the second part we want to find out tension in the rope when it is at highest velocity. So these are the two things we want to do here. Now what we are going to do is that what else information is given is this angle is 60 degree and this angle is 15 degree. That's the information is given. So we are going to use this principle here. We have initial velocities, initial kinetic energies and potential energies equal to final kinetic energy and potential energy. So here at this point it has some potential energy, it will have zero kinetic energy, and as soon as I drop it, all that potential energy will be converted into kinetic energy. For that I'm going to, my objective is to calculate final kinetic energy. If I can do that, I can calculate velocity. So objective is to calculate TB. TA is 0 because initial kinetic energy is 0. VB is 0 because final potential energy is going to be 0. So it's simply VA is equal to TB. So here VA is nothing but WYA, and the rest part here VB is going to stay 0. So here it is important for me to calculate this height. If I want to calculate VA, VA is my potential energy at this point, I need to know this height. To calculate this height, we are going to use these two right angle triangles, this angle triangle and this triangle. So if you use trigonometry, what we do is that this side divided this side, this 20 cos 60, this side is subtracted from this large side, and if we do that, we can calculate h. So h is this minus this, that's my h. And then for that I'm going to use this trigonometry, and if I do that, I'll get 20 cos 15 minus 20 cos 60, and then finally I'll get total height is 9.3 meters. So all I have to do now is put this 9.3 meters here. Mass is 8,000 into gravity. I'll get this one. This one is nothing but equal to TB. Once I have TB, I can calculate V2. So that's what I do. That's my total potential energy is equal to my here kinetic energy, here final kinetic energy, and then I can calculate velocity as 13.5 meter per second. It means this plane is crashing here with velocity of 13.5 meter per second. That's it. That's your problem. The next part of the problem asks, what is the tension in the rope? Now this problem will become chapter 13 problem. So for calculate the tension, all you do is that draw a free body diagram. This is a tension in the spring. Normal and tangential component I'm going to use because this is taking a swing. This is a curved path. So normal towards positive here. This is the positive towards the center. Tangential towards the tangential acceleration. Weight acting downwards. Now this is a chapter 13 problem. All the forces applied in normal direction. Fn is equal to MAN. My objective is to calculate tension. It means I need to find out value of AN. AN is nothing but V square by rho. Velocity is 13.52. Rho is 20. So I can calculate AN. I'm going to take that value of AN here. I can calculate this Fn, all the forces in normal direction. I'm going to do that. So T normal positive, weight W sine 15 negative, W cos 15 downward, so it's going to be negative. I'm going to write that down, is equal to An, mass 8000 into An is this one. I have all the one equation, one unknown. I can calculate final value of tension. That's just like we do in chapter 13, 149 kilonewton, and that's it. So that's my tension in the rope at its maximum velocity. This is very simple problem. This one is a solved problem from the book. Solve that problem, and that's pretty much we have in this chapter. That's your end of chapter. I'm going to put some practice problem here, and those practice problems you can solve at home later, and those practice problems are there already on the blackboard. Anyway, so I'll stop here right now. That's your chapter 14, work and energy. We'll continue our discussion in the next video with chapter 15, impulse and momentum. Stay safe.